Well, hey everybody, I just wanted to check in with you here after a busy week of doing vector spaces. There's a lot of material that we're trying to learn and it gets kind of abstract. So I thought, in case you need a little extra help with the concept of spanning sets, that I would give you a quick little video, kind of show you what kinds of questions you might get asked and go through the procedures of how to answer those questions for a couple of examples. Okay, so hopefully these will be helpful to you. I'll try to make it quick. Just to remind you again, a set of vectors is a spanning set for your vector space V if, when you take the span of those vectors, you get the entire vector space V. Okay, remember that the span of a set of vectors is just all of the possible linear combinations of those vectors, right? So you're taking every possible linear combination of V1 through Vn, and you're looking at what you end up with. When you take that span, you will always get a subspace. Okay, so one of the first things that you want to know about the span of a set of vectors is it definitely gives you a subspace. It's closed under addition, and it's closed under scalar multiplication. If the subspace that it gives you is the whole big universe vector space V that you're working in, then that set of vectors that you started with is a spanning set. Okay? So one of the types of questions that you'll get asked regularly about this material is that they will ask you to come up with a spanning set for something. So, for example, it's very easy for our familiar vector spaces, so like R3, it's easy to figure out that a good choice of a spanning set would just be 1, 0, 0, 0, 1, 0, 0, 0, 1. Pretty easy to see that every vector in R3 can be broken down in terms of these three. Okay? Here's another example, P4 of R. Polynomials of degree 4 or less. Every one of those polynomials of degree 4 or less can be broken down as a linear combination of these different powers of x from 1 up to x to the 4th. So those are pretty easy. If I ask you for a spanning set for R3, here's a good one to use. If I ask you for a spanning set for P4 of R, here's a good one to use. Okay? It's not the only choice. There can be many different spanning sets for a vector space, but these are kind of the natural ones here. Now, sometimes our vector space is not quite such a standard vector space. So instead of Rn or Pn of R or something like that, we might be looking at a different kind of vector space and be asking for a spanning set. So I just want to run through a couple of examples that are of that nature for you. So here's one. It says, find a spanning set for the null space of this matrix. Remember that the null space of a matrix is a vector space. It's actually a subspace of Rn, where n is the number of columns of the matrix, right? So it does form a vector space in its own right, and so therefore we should be able to find a spanning set for it. Okay? So the way that you do this problem is you basically take the matrix and you first figure out what is the null space. And once you know what the null space is, then you can go ahead and find a spanning set for it. So we have to do EROs. Let me just call this matrix A. And I am just going to skip all of the ERO steps because I don't want to dwell on that part of it. And let me just show you the row echelon form that we get. Remember, for the null space of a matrix, we are setting these equations equal to 0. Remember, you're looking at solutions to the system AX equals 0. So I'm adding zeros over here. And when I row reduce this thing, what I'm going to get, let me just get my notes here, it's just going to be 0, 1, 2, and then 0, 0, 0. Okay, so just take my word, if you just do a couple steps of EROs, this will be your row echelon form. Notice that my z variable is unpivoted if I think of these as x, y, and z here. So z is free. I'm going to call it t. And then if I back substitute using the second line, I find out that y is negative 2t. And then if I plug that into the first line, I get that x is equal to t again. Okay, so we have t, negative 2t, and t. So that just means that the null space of A is equal to the set of vectors of the form t, negative 2t, t. Okay, where t is a real number. That's the null space of A. Okay? Hopefully so far so good. But that's not a spanning set. Okay? The way you get a spanning set for this collection of vectors here is you do what I like to call bust out the variables. Okay, we're going to bust out the variables. In this case, there's only one variable, which is t. If I bust it out, so I'm going to bust out the t, it leaves me with 1, negative 2, 1, right? Factor the t out of all three of these slots here, right? You factor it out, these are the numbers that will be left in those slots. This, my friends, is the spanning set, right? If I take the span of this, what am I doing when I do that? Well, I'm taking all linear combinations of this one vector, which really just means I'm taking all scalar multiples of this vector, which is exactly this set right here. Okay, so this then is my spanning set. This would be the spanning set that we are looking for in this problem. Okay, so we bust out the t from the formula for the null space right here. We bust out the t, this is what we're left with. Okay? Let me show you another example where we kind of do the same thing, just so we can practice it a little bit more. Suppose I ask you to find the spanning set for the vector space of 3 by 3 symmetric matrices. Okay? So, unlike the previous example where I had to first compute the null space before I could do anything further, here I already know kind of what the form of a 3 by 3 matrix is. And what we want to, I'm sorry, a 3 by 3 symmetric matrix. What we want to do is write down that form. So let's just write it down. Basically, the first row can be anything. The B has to be mirrored by B here, and then D is anything, E is anything, and then these things have to reflect. The C has to reflect, the E has to reflect, and then the lower right corner can be anything. You guys see that is a general form of a 3 by 3 symmetric matrix. It would look like that. Okay? So once we have that, the process that we're going to go through to find a spanning set is the same as before. We're going to bust out the variables. The difference here is that I actually have 6 different variables to bust out of this expression. So I'm going to rewrite this as a linear combination. So I have A is multiplied by this matrix, 1, 0, 0, 0, 0, 0, 0, 0, 0, right? And then plus, I'm just going to keep going here, B gets multiplied by 0, 1, 0, 1, 0, 0, and 0, 0, 0. And then C gets multiplied by 0, 0, 1, 0, 0, 0, 1, 0, 0. Right? We just keep going like this. D gets multiplied by 0, 0, 0, 0, 1, 0, 0, 0, 0. And then E gets multiplied by 0, 0, 0, 0, 0, 1, and 0, 1, 0. And F gets multiplied by 0, 0, 0, 0, 0, 0, and 0, 0, 1. Okay? So, whoops. So that is breaking the matrix down, the arbitrary element of V. Right? We took a random, arbitrary looking element from V. A 3 by 3 symmetric matrix has this form. We took it and we busted out the variables. We factored them out is really what we did. Right? We pulled out the A and we said, okay, if we take out the A, what are the things that are left inside the matrix where those A variables appeared before? Right? And we do the same thing with B, C, D, E, and F. So what you end up with then is a spanning set. In this case, you have actually six different matrices, right? So you have 6 different matrices here in the spanning set. So let's just write down the answer. Spanning set equals, okay, so the first one, I kind of just have to write these all down again. 1, 0, 0, 0, 0, 0, 0, 0, 0. Then the next matrix, I'll do this really quickly. You can always fast forward me if this is too boring for you. All right, so I just have to write all of these down. The next one would be that. And then I have two more to go. 0, 0, 1, 0, 1, 0. And the last one is this one right here. Okay, so we have 6 matrices in the spanning set for all of the 3 by 3 symmetric matrices. Okay? So these first 2 examples, basically, I asked you to find a spanning set for something. The way we approached both of those examples was we wrote down what an arbitrary element of that vector space would look like, whether it's a 3 by 3 symmetric matrix or whether it's finding what the null space of a matrix looks like. And we could do other examples with polynomials if we wanted, or any other of the types of vectors that we've looked at so far in this chapter, and do the same thing. It's all about busting out the variables. Okay? So there's an additional question, a related question that we can ask that I want to spend the rest of this video talking about. So instead of asking you to find a spanning set for something, what I can do is I can propose a spanning set for something. And I can ask you, is it a spanning set? So let me show you a couple of examples of how that might look. So is the following set, I'll call it S for now. S is going to be the following vectors: 3, -6, 1, and 1, -4, -4, and 8, -14, 7. Is that set a spanning set? Is that a spanning set for R3? So this is another question we could ask. There's lots of spanning sets for R3. This one is pretty obvious over here, right? This one, I cannot just look at that and tell you if it's going to be a spanning set or not. We're going to have to do a little bit of work to figure that out. Okay? So is it a spanning set for R3? In other words, what we're really asking is, can every single vector in R3 be expressed as a linear combination of these 3? Right? In other words, the span of these 3, would it give me every vector in R3? So what we try to do to answer this kind of question is we try to set a linear combination of these vectors. Okay, I guess I'll call it C1 times 3, -6, 1, plus C2 times 1, -4, -4, plus C3 times 8, -14, 7. We try to set that equal to an arbitrary vector xyz. Okay? If you do that, you quickly realize that there's 3 equations here. If we look at the left slot of every single triple that we have, on the left slot here we have 3C1, and then we have plus C2, and then plus 8C3 equals x. And then in the middle slot, right, in the middle slot we have -6C1 minus 4C2 minus 14C3 equals y. And then in the last slot we have C1 minus 4C2 plus 7C3 equals z. Okay? This is a linear system. And the question is, can we solve it? Right? Can we solve this linear system for C1, C2, and C3? So the unknowns right now are C1, C2, and C3. And x, y, and z, these are to be thought of as given values. They are given, but they are arbitrary. We don't have specific numbers here. They are arbitrary numbers. Okay. If we can solve this system for these 3 unknowns, if we can always do it for any x, y, and z, then that will mean that these 3 vectors in S do indeed span R3. On the other hand, if this is an inconsistent system with 0 solutions for C1, C2, and C3, or at least sometimes 0 solutions, depending on x, y, and z. If there's even one choice of x, y, and z that makes this inconsistent, then the vectors that we started with do not span R3. Right? So what we have to do, of course, is solve the system. Let me just put it into an augmented matrix like we always do. Okay, so the augmented matrix is going to look just like this. Yeah, -6, -4, -14, and y, and then 1, -4, 7, and z. You know, one thing that's very interesting about this, notice the columns of this matrix here. The first column is just the first vector that we started with here. And the second column is the second vector, and the third column is the third vector. And when you're doing this process, guys, that is always going to happen. That's not just a fluke on this problem. So the original vectors that you had end up in the columns of this matrix. So you really could just shortcut. Instead of writing all this down, you could jump straight to this matrix and you would know that that's where you would end up. Okay? Now I took the time to row reduce this with some EROs, and I'm going to go ahead and just tell you what ends up happening. Okay? So what ends up happening is you get 1, 3, 8. Let's see. No, that's actually not right. I've put them in a different order here, haven't I? So, okay, that's kind of annoying. Let me just do some EROs real fast. Okay. Again, you can fast forward through me if this part is not so illuminating to you. So I'm going to put the third row first. I'll leave the second row where it was. And then I'll put the first row third. Now I'm going to go ahead and add 6 times the first row to the second row. It would be -28 and 28 and y. And then -3 times the first row. I'm going to add that to the third row. And I get 13, -13, and whoops, this should have been, sorry, this should be, getting a little flustered here. Let's see. This should be a y plus 6z. There we go. And this one should be x minus 3z. Right. Okay. I think I got it right now. Notice that what we can do is, okay, we can divide through the second row by -28, and then we can divide through the third row by 13, right? So what this is going to give me is 1, -4, -7, augmented with z, and then 0, 1, -1, and this is just y plus 6z over -28. And then the third row is 0, 1, -1, and x minus 3z over 13. Finally, I can just add, I can do a2, 3 of -1. I can basically, the first row stays the same, second row stays the same. Okay, I'm doing this quickly because this is not the key point here. So what happens in the third row, right, this is the key point. Row of zeros here, and then the negative of this added to this, so it's some messy expression here. X minus 3z over 13 minus, but actually it becomes a plus if I put the 28 on the bottom here. Y plus 6z. There we go. Notice where the pivots are. Right? There is a pivot in the far, far, far right column unless x, y, and z happen to make this equation cancel out. Okay? But for most values of x, y, and z, this is going to be a non-zero number, which means we have a pivot in the far right column, which means the answer here is no. Okay? Now in this case, the original coefficient matrix here was 3 by 3. It's a square size, and when we do our EROs, we end up with this matrix that has a row of zeros in it. Really just means that it's not invertible. So when the matrix has a square size, you can answer these spanning set questions by just looking at whether the matrix was invertible or not. Now, not every problem is going to have a square matrix to it. So you do need to be able because if the matrix isn't square, you can't take a determinant of it, right? So you do need to be able to go through the ERO process and look at the pivots. If there's a pivot in the last column, it's more important to look at the pivots than even looking at where the rows of zeros come in. Turns out the pivots are the key to everything, because that's what determines whether there's no solutions, one solution, or infinitely many solutions. Okay. Now notice that if x, y, and z, this is actually the equation of a plane here. It looks a little messy, but if you cleaned it up and simplified it, this is just the equation of a plane. And if you set it equal to 0, then in that case, there would not be a pivot here, and that would mean that it is consistent. It just means that there are some x, y, and z choices. There are some points, x, y, and z, that you can span with the 3 original vectors. It's just that you cannot span all of R3. You can't get every point of R3 just using these 3. Okay? And it's not surprising that this forms a plane. If you set it equal to 0, it forms a plane. It just means that these vectors span not all of R3, but they do span a plane, a 2-dimensional plane that is inside of R3. There's really no surprise there. Okay? Now hopefully that example makes sense. Let me show you one last one, and then I think you guys are going to be able to really make some good sense of this section. I'm going to give you one more proposed spanning set for something, and we'll see if it actually works. Okay? So this is example 4. Okay, and here's what it says. Is the set 1, 2 plus 3x, and 7 plus 8x plus 9x squared plus 10x cubed. Okay, actually let's make this a 1x cubed, just x cubed here. Okay, so just take that. Are these 3 polynomials a spanning set? Yes or no? Is this a spanning set for P3 of R? So we'll do an example with polynomials. So the question really is asking, can every polynomial in P3 of R be expressed as a linear combination of these that are written here? So we do the same process that I did on the previous example. We take a linear combination, let's say C1 times 1, plus C2 times 2 plus 3x, plus C3 times 7 plus 8x plus 9x squared plus x cubed. And we're going to set that equal to some arbitrary, random, but fixed polynomial in P3, like a cubic polynomial. So I'm going to write it as a plus bx plus cx squared plus dx cubed. This looks like one equation, but it actually can be thought of as several equations. Because look, if I break down the constant terms, here's C1 plus 2C2 plus 7C3. Those are the constants, right, of each of these parts. And then what are the x parts? Well, there's a 3C2 here and an 8C3 there multiplied by x. Okay? And then what about the x squared parts? Well, there's a 9C3 that's multiplied by x squared. And then the x cubed part is just C3 itself, okay, times x cubed. And we're setting that equal to a plus bx plus cx squared plus dx cubed. When you're working with polynomials, you kind of want to match up the coefficients on the left side with the coefficients on the right side. Okay, so the question is, can we make this polynomial, can we choose C1, C2, and C3 so that it equals this polynomial over here? That's really the question. Okay, so again, we actually have several equations. The constant term here, C1 plus 2C2 plus 7C3, has to equal A, right? And then the next equation, 3C2 plus 8C3, has to equal B. That's the x term on the left side matching up with the x term on the right side. And then the x squared term is 9c3 has to equal c. And then the x cubed term is that c3 has to equal d. You get another system of equations, right? You can put this into a matrix again. 1, 2, 7 augmented with A, and then 0, 3, 8 augmented with B, and 0, 0, 9 augmented with C, and 0, 0, 1 augmented with D. Notice the coefficient matrix here is not a square size. We cannot use the determinant to help us this time around, okay? But what you're going to notice is that, okay, I can row reduce this one. I can row reduce this one. Let me not even worry about the first two rows too much. But if I switch the third row and the fourth row, that's a 9. So I'm going to permute 3 and 4. And then if let me just come back up here so I can make sure this is getting on the video. Now if I do, A3, 4 of -9, okay? First two rows, whatever they are, but the third row, 0, 0, 1. So we have, basically, we're going to have pivots here, here, and here. But then the fourth row, when I do A2, 3 of -9, is C minus 9D. And that might not be 0, right? That could be, unless C and D are very, very related to make that come out to 0. In other words, C would have to equal 9D. If that's not true, then we have a pivot there, and it's inconsistent. So we have to say no again, right? If there's even one choice of C and D that forces this number to be non-zero in that far, far, far right column, then we don't have a spanning set, because there are going to be some polynomials, right? Some polynomials where the C and D make it impossible to avoid this pivot going into that last column. Okay? So we've looked at two types of problems tonight. I hope that this makes sense. The first one is find a spanning set for a particular vector space that you might be given. Okay, so you want to be able to do that. And then the second thing you want to be able to do is, if I give you a proposed spanning set, and I ask you, is it a spanning set? You have to do a little bit more work sometimes. It usually involves solving some system of equations here. But the issue is, can you solve it? Is the system consistent, or is it not consistent? We don't actually have to solve the system, by the way. Notice I'm not doing any back substitutions here or anything else. I'm simply trying to get a thumbs up or thumbs down as to whether there is any solution at all to the linear system. Hope that this makes sense. This is just a brief overview again, a little more practice on spanning sets. I hope it makes sense, and if there are any questions, be sure to let me know. Thank you.